Hello everyone, today we'll go through chapter 15 which is on simulation, which is imitation of a real event or an activity. So simulation is actually very popular in many industries, and there are several advantages which simulation can provide. So it allows like what if kind of evaluations at a very low cost. Just by changing some parameters or numbers, you get the outcome like what if you did this, what if you had like three stations instead of two, what if arrival rate becomes more or less. So it helps to reduce the cost in assessing different situations. And nowadays we have a lot of softwares available which can help to do like very complex kind of simulations in no time. So this is something which is really useful, and it's a very good skill to have, ability to develop some simulation modeling. There are different types of simulation models, and mainly they can be classified in three categories. First one is called, and which is very popular, is Monte Carlo simulation. Second one is operational gaming, and third one is systems simulation. So if you look at the first one, this can be used in situations involving probability or chance. So those situations where the outcome is uncertain or probabilistic, so in those situations Monte Carlo simulation could be used. Now the second one is operational gaming, and as the name suggests, it is about competitions, and it involves two or more competing players. Third one is system simulation. So this is about very large systems. So each one has its place in simulation modeling. But in this chapter, we are going to mainly concentrate on Monte Carlo simulations where situations involve probability or chance. When we make these models, simulation models, we also need to verify and also validate those simulation models. So verification is an important step, and it basically means asking a question that did we build the model right? So this is obviously very important. The model has to be right. It should capture the reality or the activity it is imitating as much as possible. So obviously there will be some losses in terms of it cannot be like 100% match because it is simply a model, but we have to get more or less most of the factors right. And validation is asking a question, did we build the right model? So actually same situation can be modeled using different methods. So whether we used the right model to represent the real event or the activity. So these are like very important steps. If they are not answered properly, obviously whatever outcome we get from simulation models may not help to optimize, or it could also increase the cost because we may be implementing something which is obviously not correct. So in this chapter we will look at different examples involving Monte Carlo simulation. So number 15 says the number of cars arriving per hour at this car wash during past 200 hours of operations is observed, and the data is given. So the data you have is on number of cars arriving and also frequency, like how many cars arrive. So the question being asked is set up a probability and cumulative probability distribution for the variable of car arrivals. To convert this data into probability, it is very simple. You create probability column, and what you do is divide this 20 by 200. So 20 divided by 200, you should get 0.1. 30 divided by 200, you should get 0.15. 50 divided by 200 is 25%, so 0.25. 60 by 200 is 30%, so that the total probability is 1. So from this we create cumulative probability. 0.10 plus 0.15 is 0.25. So we are adding these two and repeat the same thing as you go down. So 25 plus 25 is 0.50, 0.80 and 1. So how to do this? It is very simple. You have to look at the cumulative probability column and note that the first value is 0.10. So what we'll do is we always start with 1 and the interval goes up to this 10, so 10. So because it goes from 1 to 10, the next row we start with 11 and this will go up to this value is 0.25, so we just multiply 0.25 by 100. This starts at next number 26 and goes to 50 because this is 0.50. This one starts with 51 to 80, 81. Now 81 to it should be 100, but for simplicity we just write down 00. This is the convention we are going to use for all the problems related to simulation. So with this we are ready to do simulation. So if you look at the question, part A was set up probability and cumulative probability distribution. We have done that. B is establish random number interval for the variable. So we just now did that. Now part C says simulate 15 hours of car arrivals and compute average number of arrivals per hour. So we have to simulate 15 hours of car arrivals and see what we get. Car arrivals, and this is obviously in hours, and we have to generate 15 hours of car arrivals. So 1, 2, 3, 4, 15. Now to do this we have to use random numbers because the car arrivals is probabilistic, or there's a chance. We cannot guarantee like how many cars will arrive at a given time. So to generate 15 different situations, we use random numbers. Now for random numbers, you can refer to the random number table in this chapter. I think the table number is 15.5 and this is on page 632. This is how this table looks like. So you can see it starts with 52, 37, 82 and so on. You can start actually at any position. So let's start at the beginning. So 52 and copy first 15 random numbers starting with 52, then 37, then 82 and so on in second column. So I'm going to write that down and then we'll see how to use this. So these are first 15 random numbers from that table. So just for simplicity I started in the first column. In reality we could have started anywhere because this is a totally random number table. You can start anywhere. You can go from top to bottom, left to right, or right to left, or bottom to top and so on. It doesn't matter. Let's create one last column which is called simulated number of arrivals. Now how to generate simulated number of arrivals is very simple. Look at the first random number. So it is 52. Now locate in the random number interval where this 52 will lie. So it lies between 51 and 80. So the corresponding number of cars arriving you can see is 7. So I'm going to write 7 here. Next random number is 37, and 37 will be between 26 and 50. So arrivals in the second hour will be 6 cars. Next one is 82. So 82 is obviously between 81 and 100. So number of arrivals will be 8. So this way you repeat for all 15 hours, and this is what you get. So if you add the total simulated number of arrivals, we get 105. So based on this, we can say average number of arrivals per hour will be 105 divided by 15, because there are 15 hours and the total arrivals are 105. So this is 7 cars. So on an average, using this simulation, we can say on an average the number of car arrivals per hour will be 7. So all these calculations you can see are based on the data. So the data was number of cars arriving and the frequency, which we converted into probability. So obviously if the frequency changes, all the simulation we do will come out with different outcome. Now if you recall from operations management class POM 345, we had a concept of economic order quantity, EOQ, and one of the assumptions for arriving at EOQ is that demand, so this is the forecasted demand, and lead time are constant. So this is one of the assumptions, but most of the times this assumption in reality, in practical situations, may not hold. So when you have a situation where demand and lead time varies, obviously we cannot use that formula for EOQ and do the calculation. Instead we can make use of simulation. So this is the Moore Appliance Center sells and services several brand of major appliances, and past sales for a particular model of refrigerator have resulted in falling probability distribution for demand. So this data is given. You have the probability distribution of demand per week, as well as you have the lead times. And you can see because you have the probabilities, that means there is a variation. So let me write down. So I'm just repeating what is available. Now how this probability number was arrived at is very simple. If you look at the example we did just now, so when we calculated this probability, it was based on number of cars arriving and the frequency. So for frequency, we use the total frequency, and each number was divided by the total to get the probability. So in future problems and examples, actually straight away probability is given, but you can assume that it is based on historical data where somebody collected data on the frequencies and then converted that into probability. So next steps are very straightforward, and the last one is 0, 0. We don't write 100. Similarly, you have data on lead time, 3 weeks of lead time maximum and minimum 1, and then you get cumulative probability. The data given is order quantity. Whenever we order, that quantity should be 10, and reorder point is 2. Now we make a simulation table for this inventory analysis. So this is a bigger table. So we have to simulate for 10 weeks. These are the standard columns which I am making. So you have week. So we are doing this simulation for 10 weeks. We always start with the units received 0, and beginning inventory, the problem says is 5. Now for modeling or simulating demand per week, we are going to use random numbers. So what I would suggest is we use the first column starting with 52 for the demand simulation, and then when needed for lead time we can use the second column. So let me do this. I will write down the first 10 random numbers. So if you look at the demand per week, so first number is 52, random number is 52. So 52 lies somewhere here. So that means demand per week is 1 for the first week. Then we have 37 which also lies in the same range. So demand is still 1. Next is 82. So 82 lies in this range. So demand per week will be 3. So if you follow this for all 10 weeks, you should get. So demand in first week is, you can see, 1. And we are starting with 5 refrigerators in the inventory. So after filling the demand, ending inventory will be 4 because 5 minus 1 is 4. And we don't lose any sales. And order, obviously no, because we still have 4 in the inventory. So then we move to next week. So we have not received anything because we have not ordered anything in the second week, and the beginning inventory is 4. Because demand is 1, so we will be left with 3, and we don't lose any sales. We don't order because reorder point is 2 and we still have 3, so answer is no. So we enter third week with receiving nothing and 3 refrigerators as a beginning inventory. So now it gets interesting because your beginning inventory is 3 and demand is also 3. So you are going to be left with 0. You don't lose any sales in this week, but because the ending inventory is now 0, which is below this 2, we should order. So answer is yes. Now because we need to order, we have to figure out what will be the lead time, and for that, as I mentioned earlier, let's use the second column. So 0, 6, 6, 3 and so on. So first random number is 0, 6 in the second column. It lies in this range. So we are looking at the second table now for the lead time. So because it lies in the range 1 to 15, lead time is expected or estimated to be or predicted to be 1. So that means if we order this week, it will arrive after 1 week. So arriving after 1 week simply means you will not get anything in week number 4, but the arrival is going to come in week number 5. So in week 4 your beginning inventory is 0. Demand is 2. You have nothing in the inventory, so ending also is 0, and lost sales now is 2. Now although our ending inventory is 0, but we don't order anything because we just ordered in the last week, which is going to arrive in the next week. So order is already in place, so we don't order anything in the fourth week. Week 5 we start with these 10 refrigerators which arrived, but the demand is 4, so we are going to be left with 6. Nothing lost in terms of sales, and we don't order anything because we still have 6 left. So we start with 6, again demand is 4, we are going to be left with 2 now. No sales lost, but because we are left with 2, which is the reorder point, so we have to order again. And the next random number in second column is 63, and 63 is in this range, so lead time is estimated to be 3. So because every time we order, we can order 10, So this 10 will arrive, we are ordering in week number 6, so after 3 weeks. So 7, 8 and 9 are gone, nothing arrives there, but this 10 arrives in the 10th week. So we start week 7 with inventory of 2, demand is 1, so we are left with 1. We don't lose any sales, we don't order because we just now ordered. 8th week, we are left with 1, demand is 1, we don't lose any sales, and we do not order anything because we have already ordered 10 refrigerators. So week 9 we actually have nothing to start with, demand is 3, nothing in terms of ending inventory, we lose 3 in terms of sales, we do not order because we have already ordered. Now 10 has arrived in week number 10, demand is 3, left with 7, 0 and nothing. So this is the simulation for 10 weeks. Now we can do some calculations to see the performance. So what you can do is you can add the total ending inventory. So this is 23. So based on the information or the data given in the problem, you can do this calculation. So this is coming from the data, $40 times 5. So this 5 we got is equal to $200. So because the cost is $1 times 23, which is this number, is $23. So this is equal to, so because this was for, total is 223 and this was for 10 weeks, we divide by 10, so it is $22.3. So in a week we are losing $22.03. So multiply by number of weeks in a year, 52. So you should get, so this is the total yearly cost based on this simulation. You can see this simulation is very straightforward, and the model, like the formula we have for EOQ, doesn't work in this situation where we have the probabilities for demand and lead time. So simulation comes to our rescue and helps us to obtain all these costs. You can always play with the reorder point or order quantity and see what if, say, order quantity is 20, or what if order quantity is 5, what if reorder point is 1, or what if reorder point is 10. So under different situations we can very easily calculate what will be the cost and what will be the best way to minimize the cost.